Hello, my name is Olivier Nijs and I'm a PhD student at Ghent University in Belgium. Today I'm going to present to you my results concerning the effect of deformation on hydrogen-induced cracking. So the phenomenon I study is blistering. An overall theory is accepted for this phenomenon, being the internal pressure theory. So this says that hydrogen can enter the material, will collect at certain depths, and then recombination of the hydrogen can occur, forming hydrogen gas, which leads to pressure buildup in the material. This then can lead to cracking, and if the phenomenon occurs at the surface, the cracking will result in like a blister shape. So the surface is pushed up, and you get like blisters on your surface. This phenomenon can occur with no external stress, so it's purely due to the mechanism of hydrogen. In Belgium we have like a perfect example of this phenomenon, since we found like hydrogen-induced cracks in our nuclear power plants. So it's quite a critical situation, and it's important to better understand the mechanism. Do I hold it wrong? I don't know what I'm doing wrong, sorry. So it's critical that we understand the mechanism, and that's also my goal. So I perform studies on a fairly simple material, being ultra-low carbon steel, to study like quite fundamentally this phenomenon. And what I want to understand more is the effect of deformation of a deformed microstructure on this phenomenon. So I use ultra-low carbon steel, with just a purely ferritic phase microstructure. We processed oval shaped discs from sheet material, and we worked with like ground surfaces. We chose three deformation or material conditions. So first we cold rolled the steel to 60% reduction, and from this cold deformed sheet we annealed to have like a recrystallized microstructure, and then we also did another annealing treatment to have a partially recrystallized structure. We charged samples with current that's electrochemically, so cathodic charging, and we charged samples with a 5 milliampere per square centimeter current density, and for 2 days. We did this for the three material conditions in order to compare the different cracking behavior of the materials. We used the sulfuric acid with thiourea as a poison for the electrolyte. The obtained samples, we did a surface analysis with optical microscopy, and then we cut the samples and made a cross-section analysis by SEM and EBSD. Additionally, we performed some hydrogen permeation tests in order to measure the diffusion coefficient for the different materials. So this is a permeation cell. You have like two kinds of cells, the cathodic cell and the anodic cell, with the sample in between. And at the cathodic side, hydrogen is formed and will enter the material. Hydrogen diffusion then occurs, and then at the anodic side, hydrogen will oxidize and an anodic current will be produced. If you measure this current and plot it in function of time, you get like an idea of your hydrogen diffusion in your sample. So my results for the surface analysis, I found that with like an increasing amount of deformed microstructure, you saw like an increased number of blisters. Also the size of the blisters were increased, and the range of blisters were also strongly increased. So we see that like the deformed microstructure results in like more blister initiation and also easier propagation of the different blisters. We also the blister morphology change. So recrystallized samples showed like dome-like, well delineated blisters, while cold deformed samples showed more like flattened blisters, which were not that well distinguishable. And additionally, we noticed that the blister-on-blister phenomenon was occurring. So this is all the small blisters here on a larger blister. So it's a kind of secondary blister formation mechanism where small blisters prefer to initiate on already existing larger blisters. This was not observed. This was not observed for the recrystallized material, but it was for the partially recrystallized material. Then the results of my permeation test. So here you have the current and function of time. What you see is that for the recrystallized material, hydrogen passes really quickly through the sample, and with partially crystallized, it's like retarded a little bit. But then for cold deformed material, the breakthrough time is increased, and also the slope of your curve is lowered, so it takes hydrogen a longer time to get through your sample. If you calculate from this curve the diffusion coefficients, you get these values, and we see that the diffusion coefficient is much lower, a factor 10 lower for cold deformed material in correlation with recrystallized material. And this can in fact be explained by the deformation will induce hydrogen traps in the material. You form dislocations, vacancies, and low angle grain boundaries, and these all have a certain interaction with hydrogen, which induces diffusion inhibition, in fact, of hydrogen through the material. The diffusivity and also the solubility of the deformed material is much higher than for recrystallized material. So what we see is that the blister sensitivity rises considerably due to the higher amount of hydrogen traps. Also, more blister initiation sites are present, so dislocations, low angle grain boundaries, and vacancies can act as blister initiation sites. And additionally, we see the blister-on-blister phenomenon. If we then look at cross sections, we found this result. So what they had in common, the different materials, was that the cracks mostly went like parallel to the surface, and also the crack tips often deviated towards the surface. So this is kind of an indication of the internal pressure theory, because cracks will move towards the surface to release their internal pressure. Additionally, we saw that in fact the cracks, for all cases, were not like common known single cracks, but existed out of interconnecting branching small fine hairline cracks, and always recombined to form like one bigger crack entity. What we saw as a difference was that the recrystallized material, the crack thickness was thicker, and it decreased when we went to a more deformed structure. And also we saw like some more empty space in between the different small cracks than for cold deformed material. This also corresponds with the shapes that we see at the surface. You have the nicely delineated cracks of blisters for recrystallized materials corresponding to the thicker cracks. If we then look at the EBSD analysis, we see that for recrystallized material, we have transgranular crack tip propagation, and also you get like the pieces of grains that are enclosed into your crack. If we then compare with deformed material, we see that it's also a transgranular cracking, but what is observable is that here you see like some slip lines or slip lines in the grains which accommodate the high deformation, and your crack really follows like the slip lines in a step configuration. So these slip lines are high dislocation planes, and since dislocations trap hydrogen, these specific lines are like more embrittled, and the crack will propagate more easily through these slip lines. If we then look at a more evolved crack, so already one that has been branching and reconnecting again, we see the overall matrix is quite deformed because we're working on deformed material, but we see that the misorientations in the crack are even higher. So this again implicates the internal pressure theory, where the pressure pushes and induces strain into the material that is surrounding the crack. So my conclusions is that the strain-induced effects have a strong enhancement of the sensitivity to hydrogen-induced cracking. The solubility and diffusion is strongly affected, and a lot of this initiation locations are induced, and also due to the high density dislocation planes, cracking occurs more easily, making cold deformed material much more sensitive to hydrogen-induced cracking than recrystallized material. Thank you, and are there any questions?